So today, how many people, first of all, know or have heard of RFSoC or RFSoC? People say it different ways. Some people have, yeah, okay. Anyway, as you know, Pentek is a board-level company that has produced software-defined radio boards, A to D, D to A converters, FPGAs for many, many years. Typically what we do is we come out with the latest products based on the latest devices from people who make FPGAs or A to D converters or maybe even processors or DSPs. We put them together. This presentation is going to be talking about a new kind of product that does those functions in a completely different way for the first time. So let's take a look. First of all, RFSoC stands for radio frequency on a chip. What we're going to do is look at what that is. It's a product of Xilinx, and it's getting a lot of attention. We're going to look at some market opportunities, the challenges of designing with the RFSoC chip, the module concept that we're proposing, and then how it can migrate to different form factors, and then we'll just do a summary of it. So first of all, let's see, where did this first come about? In February, almost 2 years ago, Xilinx announced the RFSoC chip, and it was quite a lot of big news. And it combines the RF section with a MP, or a multi-processor system on chip, which has been around for a while, but putting everything into a single chip. So this was announced as something that was, you know, breaking all kinds of disruptive integration, architecture, and all these big fancy words, and in fact, it really is. And I'll try to show you how and why. So it's built on the Xilinx UltraScale Plus fabric, which is their latest fabric. And what it has as a basic FPGA engine is the DSPs, high performance I/O, general purpose I/O, block RAM, internal RAM, memory controllers, gigabit serial lines that run at 28 gigabits per second, which can support 200 gigabit Ethernet interfaces right into this chip. That's quite a bit, and the Mac engine is built in as a hardware resource. But that's just the beginning. In addition, Xilinx has integrated into the same monolithic device A to Ds and D to A converters, 8 of them, 8 channels of A to D, 8 D to As, and these are quite respectable devices. The A to D converters run at 4 gigasamples per second, and the D to A converters run at 6.4 gigasamples per second. That's all inside the same chip. But wait, there's more. There's a complete multi-processor ARM system built into the same silicon. So what's in there? Well, there are 4 of the Cortex A53 ARM cores. There are 2 of the R5 real-time cores. There are resources like memory controllers, system controllers, a security module, platform management, we've heard about that today, as well as a lot of connectivity for I/O that's typical of what a single board computer would have in a open VPX or any other system environment. So you have your I/O to the processor, which does include, by the way, gigabit Ethernet, which is very nice. So taking that and looking at what that represents is what you see if you add DDR4 memories, SD-RAMs, if you add high-speed connections for 100 gigabit Ethernet, for general purpose I/O, and for the high-speed gigabit serial lanes, you have a complete 8-channel RF transceiver system on a chip. And that is really what the remarkable announcement that Xilinx made back in that February announcement in 2017. So of course, this is a new part. We got to build something with it. So let's take a look a little bit at who might be interested in such a thing. Well, first of all, there's a lot of Mil-Aero applications, radars. Every radar system now is mostly a phased array antenna, where you have multiple A to D converters and D to A converters driving and receiving signals to and from the antenna for steered operation, electronically steered arrays. And there's a lot of those kinds of systems all throughout the military especially. Also, countermeasures, very fast, low latency paths from the A to D converter through some processing event like that an FPGA could do to a D to A converter to do things like countermeasures, avoid attacks, jamming, spoofing, so forth. And then communications. Communications is a two-way street. You need to receive, you need to transmit. So having both functions on the same chip with powerful processing in the middle and supervision by the ARM processor section is very important for things like tuning and management. Monitoring, interception of signals, SIGINT and ELINT as well. And then the big news that Xilinx came out with and led with was probably the biggest part of their revenue stream, which is going to be 5G wireless. Every wireless tower that you see has to do what? It has to receive signals and transmit signals, and they have to be beamformed to get the spatial diversity across the area of coverage. So, as usual, we can take advantage in our Mil-Aero niche of some very important products that are coming out to support mass markets like 5G, for example. So how does it change our market? Well, if you take a look at what's inside, if you take the ARM processor, you take the A to D converters and the D to A converters, and you take the Pentek UltraScale Plus FPGA, if you take them as separate, discrete devices, and you compare them to the size of the 40 millimeter square RFSoC chip, you're getting at least a 50% reduction, probably a little bit more in terms of space. You also get reduced power because the connections that have to be done between the A to Ds and the UltraScale no longer exist because they're already on the chip. So all the interconnect power is eliminated. You have cost savings because it's a more efficient, more economical implementation, and it's very low latency compared to most other solutions which are now using JESD 204 links in the A to D and D to A converter interfaces. So what does all this mean? What can it do for us? It allows us to take this smaller package and move it up closer to the antenna. We've been talking about getting closer to the antenna for many years. It gives us the wideband links we need with those high bandwidth A to D converters. It results in all the things that SWAP brings to different military platforms, better performance for longer missions, for more resolution, for better dynamic range, the lower latency for countermeasures, and then it also opens up completely new applications that were previously not possible because the alternative solutions were just too big, took too much power, too much space. So this is the lure of the RFSoC chip. But the RFSoC chip isn't easy to use. You can see it's quite a monster if you look at what's inside. These are the pins of the package, the 40 millimeter square package, and what you've got is 16 very high bandwidth lines for the RF analog inputs and outputs. You have to watch for interference, crosstalk, spurious pickup. You have to maintain the signal purity of these signals in the midst of a lot of other digital signals. You have to be very careful with your clocks. Clocks are as critical in terms of signal purity as the RF signals themselves. We have gigabit serial lanes for PCI Express Gen 3. We've got the 28 gigabit lanes for the 200 gigabit Ethernet. These are, very high speed. They radiate a lot. You have to tame those signals to avoid contamination. The chip requires 13 different power supplies, okay? That's really convenient, right? So some of them have to be very heavily filtered. Some of them have to be, very well regulated in terms of accuracy. The ARM processor has I/O, which includes the 1 gigabit Ethernet, and then it supports 2 banks, one for the FPGA and one for the ARM processor of DDR4 memory running at 2,400 megatransfers per second. So you've got this, and then you've got, some thermal management you have to take care of. dealing with all of these design issues and maintaining the signal integrity of all of those signals without having them interfere with each other or contaminating each other is a big job. It's hard. So we really ask our customers, what do you want? What can we do to help you get from this chip, which you like, to wherever you're going in the most efficient way? How long is it going to take a customer to deal with all these issues if he makes his own board? If we make a board for him, is it going to meet his requirements? And how can I cut my development time? So we had feedback from customers that said, this is really great, but I need something that's small because I've got to go into a small space. We've had other customers that say, I need it on a VPX board because I'm going into an embedded system. So we had a lot of different answers. But many of these customers wanted something that they could put into a very small, limited space environment. And so we tried to figure out how can we get this product into the hands of our customers so they can take advantage of the chip. So we came up with an idea. What if we were to follow a lot of the standard practices in our industry for many years and make some kind of a mezzanine card? Unfortunately, the mezzanines that we're making now, the FMC and the XMCs, really don't lend it very well to the extreme amount of I/O that the RFSoC chip presents. It's a very challenging device, as you can see. So we came up with an idea. What if we made a small module that took all the hard parts of the infrastructure to support the care and feeding and the connectors for the RFSoC chip and kind of abstracted it into a little bit easier form factor? So adding connectors, adding 13 power supplies to this so that you only need to bring in one 12-volt supply, including the memories, interfacing to the memories, doing all of the design signal integrity analysis of all of the critical signals that go in and out of the chip to maintain the signal integrity and performance of the gigabit lines, clock management, health monitoring, and to give our customers kind of a head start on all of the most difficult challenges of designing with this chip. So we said, well, okay, let's see, what could we do if we had such a module? So first of all, because we love VPX and this is our world, let's see if we can come up with a package that would take advantage of the latest VITA specifications for VPX, and lo and behold, the gigabit lanes for our dual 100 gigabit Ethernet could very nicely use the VITA 66.4 because that's what it's made for. And look at this, the VITA 67 RF input output on the rear panel. I mean on the back plane rather. That's another really nice advantage. VITA's got you covered. And then the new standards that were adopted for VITA 65.0 and 1 back in 2017 give us some really nice radio clock distribution that allows us to synchronize multiple boards in a slot, which is essential for any phased array application. And a lot of other things that new standards for optical and for RF were developed as well. So this could be used then as an open architecture 3U VPX module with this RFSoC, taking advantage of the VITA 64 on the backplane, and you've got a complete functional subsystem, which includes effectively the single board computer because of the ARM processor, the analog I/O, and the FPGA processing all in a single 3U VPX module and with synchronization across. But you could also take advantage of some of the rear panel I/O that VITA 67 brings. So instead of having front panel I/O, as we did in the previous product, we could move those signals out through a VITA 67 backplane connection for both the optical and the RF signals. And now that simplifies your system integration because you get rid of these cables that are a maintenance issue for many systems. Front panel I/O is sometimes not even possible in some systems. You could even put this module on a PCI Express carrier, and now you have a low-cost development platform that you could do, software development or even deploy it in a benign environment where you don't need the full mill rugged specification. But the thing that interested many of our customers much more was migrating it to their own custom platform. So what we could do is we could give them a standard platform like 3U VPX and say, okay, start with that, you do your development, we'll give you some help and let you get all the information, the design rules to use the RFSoC on a custom platform that you design yourself. It could be any shape, and this is one example, let's say of a small single RFSoC module, and you keep the standard 3U VPX board for development as you go along for testing. What you can do with such a small module, for example, is put it into a sealed enclosure, and then with the suitable connectors on the edge of the board, bring in dual 100 gigabit Ethernet optical lanes. You could have your command and control coming over gigabit Ethernet and 12 volts power going up into the board. This can be then mounted up on an antenna mast, for example, near the antenna with the RF signals going right immediately to the antenna circuitry and the rest of those signals coming down the mast with a complete solution for an 8-channel RF transceiver that's small and designed to meet those requirements in that environment. We also have customers who just can't get enough channels. 128-channel system, a 256-channel system. This is really where the RFSoC really benefits. And so the point there is somebody who, let's say, has a 64-element antenna could take a single printed circuit board, a custom board that they make, put 8 of these RFSoC modules on it, and put it behind an antenna array like this, and have all of that processing right up there by the antenna and behind the antenna to eliminate a lot of cabling that otherwise would be necessary. So these are the kinds of applications that our first customers told us about. And then we had other customers who said, gee, I really, now that you have this, we can really put this into a UAV. We have one customer who's putting it into a missile. We have other customers that want to put it in an aerostat, a balloon. Small vehicles, military vehicles, UAVs, drones, so forth. So it really has a lot of different places to go. So this concept is not really just a concept. I have to admit, finally, at the end of the presentation, it is actually real. And so here it's what it looks like, 2.5 inches by 4 inches, and it really takes advantage of the latest technology in printed circuit board design and layout, and it abstracts away a lot of the difficulty, giving you the analog circuitry, I/O, the RF SoC RF signals here, the digital signals over here, to give you a complete solution in this module. So it's real. We offer a design package documentation for anyone who wants to take the module and move it into their own custom platform like the ones we've talked about. It includes artwork for our 3U VPX carrier and all of the rules, the design rules to let it get you going as quickly as possible. So, last slide. Xilinx really did the industry a big favor in coming out with this new technology device. We want to make it as easy as possible for our customers to get it into their system, whether it's a standard 3U VPX system or whether it's a custom system that they want to involve and anything in between. So this then is the goal. We use the Xilinx Vivato tools, and the Pentek has a lot of tools and example codes and built-in working examples. The product did win Best in Show award at the AOC show just last fall. So we're getting a lot of really good response from the market and the community.